Hello, this is Professor Matt Katroulis of Rio Hondo College. This is our first video lecture on Chapter 2, which focuses on atoms and the periodic table, and this is for our Chemistry 110 course, Chemistry for Allied Health Majors. So we're going to go ahead and start off by talking about elements. So this first little bit is mostly a review from some of the material that was mentioned in the previous chapter. So a pure sample of an element contains only a single type of atom. So if we were to take a look at some typical elements, let's say gold, if we look at a sample of pure gold, the only kinds of atoms in it are gold atoms. And helium contains only helium atoms. And in a little while we will talk about what makes a gold atom distinctly different from a helium atom, distinctly different from, say, a hydrogen atom. At the time that I am saying this, there are 118 known elements. Elements cannot be broken down into anything simpler. They are the most fundamental unit of matter that we are going to want to deal with here in chemistry. That's not to say that there aren't smaller particles, but when you get smaller than atoms, what you find is that the different parts that make up an atom are essentially the same from one atom to another. Every element is given a name and a symbol. Sometimes that can be a little bit difficult to come up with. These names and symbols have to be agreed to by international agencies. Every symbol has one or two letters in it. The first letter is always a capital letter. So if you have a symbol for an element which only has one letter, it's a capital. For example, hydrogen is a capital H, nothing else. If there is a second letter, the second letter must always be written in lowercase, and that is done to prevent us from confusing two elements together, as I'll show you in just a moment. So the symbols are going to be shown on the periodic table of the elements. Different periodic tables have additional information. Some of them have names. Some of them have what we call electron configurations, which we'll talk about in a moment. So it varies from table to table. So here's a nice simple table. And you can see that some of the elements have only one letter in them, and they're all capitalized. And some of the elements have two letters in them, and the first letter is always capitalized. Now, the reason that we do that is because, well, what if I was to put a capital N and a capital I? A capital N and a capital I would be confused with nitrogen, which is capital N, and iodine, which is capital I. So it's very important that we use a lowercase letter because that signals that it's part of the symbol from the previous letter. It is not necessary to memorize the entire periodic table. There's very little value in such an exercise. However, there are many elements which I do need you to know quickly because we will refer to them a lot in this class. And so I have listed those elements right here. There is a handout on my website which corresponds to this that has all of these elements in it. And so you want to memorize the symbols and the names with correct spelling for all of these. You do not need to know exactly where they are on a periodic table, but it certainly helps to have an approximate idea. As far as spelling goes, fluorine is probably the one that most people make the most mistake on because of the odd combination of U in front of O. What I'm going to be doing for this first section here in Chapter 2 is talking about all the different ways that we classify our elements. The majority of elements on the periodic table are classified as metals. And on the periodic table, they're going to be principally shown on the left side. The properties of most metals include the following. First, most metals are going to be malleable. And by malleable, that means they are soft and easily shaped. That might be kind of surprising to you because you might be thinking of something like hardened steel, which is certainly not malleable. But if you compare this, say, to gold, gold is a very soft metal, and to test its authenticity in the old days, people would bite down on gold coins, and their teeth would make an indentation in it because it was so soft. Other metals, like for example sodium, lithium, and potassium, are so soft that they can be cut with a butter knife. Most metals are ductile. That's probably the first time you've ever heard that word, and it'll probably be the last time outside of this course. And what ductile means is that you can take it and twist it and draw it into a wire. The best analogy I can give you for this is if you were to remember playing with Play-Doh as a kid. You could roll Play-Doh into a ball, and then you could continue to roll it into worms and make those worms thinner and thinner like spaghetti. That's essentially what you can do with metals. Make them long, thin wires. Depending on the metal, the extent differs, but most of the metals are very good conductors of electricity as well as heat. Meaning that if you heat one side of a metal rod, that heat will very easily and rather rapidly transfer all the way across the rod to the other side. And metals tend to be lustrous, and by lustrous what we mean is shiny. Every metal is a solid at room temperature, with the exception of mercury, and mercury is a liquid at room temperature. There are some borderline cases. For example, gallium. Gallium, if you were to pour it in your hand, would melt because its melting point is just above room temperature but below body temperature. So let's take a look at this periodic table, and you can see that it is color-coded by the type of element, so metal, metalloid, and nonmetals, which we'll talk about in a moment. And as I said a moment ago, all the metals are on the left side of the periodic table. This thick stair-step line is technically what is going to separate the metals from the nonmetals. And these elements we'll talk about in a minute that are colored a little bit differently. Those are going to be called metalloids, which are kind of border elements. But all of these elements over here are metals. You'll notice that the only element on the left side which is not a metal is hydrogen. So hydrogen is a nonmetal. Interestingly enough, though, there is a lot of thought that hydrogen in the core of the planet Jupiter is under so much pressure that it actually does form a solid, and that solid is in fact a metal. But since we're not going to be working on Jupiter anytime soon in this class, for our purposes hydrogen is a nonmetal. So, how are nonmetals different? Well, if the metals are on the left side of the periodic table, then of course the nonmetals are on the right side of the periodic table, with the exception of hydrogen, which I just pointed out. It should make sense that the properties of nonmetals are largely the opposite, the properties of metals where such an opposite exists. So the ones which are solids are often brittle, meaning that you can't easily shape them. If you were to strike them, for example, with a hammer, they tend to just crack. Many of them are rather poor conductors of electricity at room temperature, and when something doesn't conduct electricity very well, we call it an insulator. And they don't tend to conduct heat quite as well, certainly not as well as metals do. Many of the nonmetals are gases, and some are solids. There is only one liquid nonmetal, and that is bromine. So it's the only other element on the periodic table which is a liquid, with mercury being a metal, which is a liquid at room temperature. So the nonmetals are listed over here. You'll notice that there are far fewer of the nonmetals than there are the metals. So now let's look at these elements here that I haven't talked about: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. So the metalloids are going to be those elements there that are in between the metals and the nonmetals, and they're going to include what I just went through right there. Typically we don't include astatine all that often. I it was on that last periodic table, but we don't talk about astatine very often. The properties of the metalloids are in between the properties of the metals and the nonmetals in many cases. They are all solids at room temperature. So when we say that they are in between, what we simply mean is that they are often not as good a conductor of electricity as a metal, but better than a nonmetal. So they're just kind of right there on the border. And as I mentioned a moment ago, I'm not going to generally include polonium and astatine on this list. One element then does seem to be missing here, because you might notice that essentially all the elements that are on the left or the right side of that stair-step line are going to be categorized as metalloids. Well, aluminum. Aluminum is most definitely a metal. So even though we can usually just look at the periodic table and compare it to their positions on that line, aluminum is definitely not going to be classified as a metalloid. Here are some pictures that show some of the distinct differences between these. So here are some of the metals. You'll notice that many of them are shiny, although this picture doesn't really highlight that very much. This element here might be familiar. That is the element copper. I'm going to go down here and look at the nonmetals, and you'll see that the nonmetals are much more diverse in their appearance. So here we have purple crystals or violet crystals, and that is the element iodine. This liquid right here, this dark reddish brownish liquid, is bromine. This green gas is chlorine. This yellow powder is sulfur. And this rock-like thing right here is the graphite form of carbon. Carbon also comes in a different form, which you're also familiar with, called diamond. And we don't have any diamonds here to show you. And then here are some of the metalloids. I can't identify them off the top of my head, but there's definitely silicon in there, there's arsenic, and some others. And you'll notice they probably look more like the metals than they do the nonmetals. Let's really hone in on the elements which are particularly important to living beings. So we have many, many different elements contained within our body, but 4 of them are probably going to be the most important, at least in terms of the mass in our bodies. And so these 4 building block elements are oxygen, carbon, nitrogen, and hydrogen. Now, we know that most of our mass is made up of water, and so water is H2O, so it's got hydrogen and oxygen as well. So we find it there. Carbohydrates, which we'll talk about towards the end of the semester, all contain carbon, oxygen, and hydrogen. Some of them contain other elements. Proteins contain all 4 of these elements. In DNA, we find all of these elements in addition to phosphorus. Now, oxygen is also found in our bodies, of course, as O2. We breathe it in. We call that a diatomic molecule. Now, these are certainly not the only elements that we have in us. They just make up the majority of our mass. So it's actually kind of surprising when we list all of these elements, because there's some that you would definitely not expect. Arsenic, for example, which is highly toxic and a very common poison, is actually required by your body in very, very small, limited amounts. But you're never going to be hearing someone tell you, oh, you need to go get more arsenic in your diet. So this figure comes from your textbook on page 39, and it illuminates how we can break up the elements. So first we have our building block elements that I just talked about a moment ago. And as I said, they make up most of your human body, 96%. We're going to have what are called the macronutrients or the major minerals. Either of these terms is going to be acceptable here. And they are things like potassium and sodium, which you need to conduct currents through your nerves. Chlorine is present in very high amounts in many of the body fluids. And then magnesium and sulfur. Sulfur is present, for example, in the proteins. Magnesium also plays a role. Calcium is essential for bone, along with phosphorus. And then we have other elements over here for which we must consume, but we only need a fairly small amount. So it points out here that they are less than 0.1% of your body mass. And so you need less than 15 milligrams of each of these in your daily diet. So for example, zinc. Zinc is an element which is fairly important for some classes of proteins. Iron we know to be very important because it's needed to transport oxygen in your blood. And we could go through all of these and illuminate their needs a little bit more, but I'm just going to go ahead and leave this here and continue on. Oh, and these are called the micronutrients. So you'll remember that in the last chapter we talked about pure substances, and we said that the pure substances included the elements and the compounds. So now let's take a bit of a closer look at compounds. So you'll recall that we said that compounds are what you get when atoms come together in whole number ratios. And the chemical formula is what tells us what the ratio is and which elements are featured in it. So one of the simplest formulas would be that of water, which is H2O. The 2 tells me that I have 2 hydrogen atoms in the formula. The fact that there is no number after O tells me that there is only 1 oxygen. So the absence of a number in most cases in chemistry means 1. Here are some other examples. So sodium chloride, which is just plain old table salt, silicon dioxide, which is found in sand and glass, and C6H12O6, which is the formula for glucose. So for any given chemical compound, that ratio is always going to be the same. Different compounds can share the same formula. I know that in the last chapter I gave the example here of saying that this is the formula for glucose as well as fructose as well as galactose and some other carbohydrates and other compounds which are not carbohydrates. But we can say that any compound has a definite composition, which means ultimately no matter the size of that particular compound that you're measuring, the percent of a particular element in it is always going to be the same. So for example, in sodium chloride, it doesn't matter if you have 50 grams or 500 grams, the percent of sodium is going to be a fixed number, and then the rest will be chlorine. We have many different ways that we can represent compounds, and for right now we're going to focus on a few of the more common ones that we'll need for this chapter and the upcoming chapters, and then we'll revisit this topic in more depth when we get to chapter 10 and start talking about organic chemistry. So we can use just a simple formula here, H2O, but you'll see that that doesn't really tell us too much other than which elements are in it. It's kind of a recipe but without any directions. Here we have what's called a ball and stick representation, where each sphere is meant to stand for an atom. And which atom is which comes from these color codes down here. And the color code is should be on pages 40 to 41 of your textbook. So white is hydrogen and oxygen is red. This is another way of representing the molecules. This is what is called a space-filling model. And you'll notice that a space-filling is kind of like ball and stick, but you get rid of these bonds which hold the atoms together. You don't show the bonds. It just looks like the atom is mated directly to the other atom. I am usually going to be, if I need to see what a molecule looks like in 3 dimensions, I'm usually going to use the ball and stick representations and not the space filling so much. So now we're going to get into the anatomy of an atom. So let's imagine that atoms are like spheres. That's going to be a good model for us. In the very center of it, or its core, is what we call a nucleus. The nucleus is always going to have what we call a positive charge to it. The reason that it has a positive charge is because in the nucleus, all atoms have protons, and the protons are positively charged. Should make sense, P for positive. All atoms other than hydrogen can contain other particles in the nucleus called neutrons. Neutrons, we say, are neutral, meaning they do not have a positive charge or a negative charge. So if you have a positive charge plus a neutral charge, that's like adding 0. That gives overall a positive charge. And so sometimes we call protons and neutrons the nucleons, which means that they are the things that live in the nucleus. Now, electrons are the other fundamentally important particle in an atom, and they are negatively charged. And what we can say about those is that they orbit the nucleus throughout the atom. You'll notice that I put the word orbit in quotation marks, and there's a very good reason for that. I don't want you to think that electrons actually go around in a circle around the nucleus like the Earth goes around the Sun. Well, that's a fairly interesting basic model to start with. The way that these electrons orbit is far, far different than anything that you've probably ever imagined. The protons and the neutrons have much greater mass than the electrons. About a little over 1,800, so that's why I say almost 2,000 times there. So almost all of the mass of an atom comes from its nucleus. Protons and neutrons have a very similar mass. Not exactly the same, but very close. So this is a good model of an atom. If we go ahead and take a look, we'll see here that we're using kind of a cloud to represent the entire atom as a sphere. A given atom can have a different radius than another atom, but ultimately, if we look at the typical diameter for an atom, it's going to be on the order of about 10 to the minus 10 meters. That's about 0.1 nanometers, so very, very small. And then right there in the middle, and this picture has been blown up dramatically, we have a nucleus. And this is a very nice artist's rendering of a nucleus. A real nucleus doesn't look like this any more than a real atom looks like a perfect sphere, but it's a good visual tool to use when you're trying to think of what an atom might look like. So you'll notice in the nucleus we have protons and we have neutrons, although remember, hydrogen doesn't need to have a neutron. All the elements do. You'll notice that there are a lot of important terms in this chapter, and it's very important to be able to understand them and distinguish between them, especially because some of the terms sound very close to one another in words. One of the most important of these terms is atomic number, which we need to be very careful not to confuse with atomic weight. And the number of protons is what the atomic number is. So we symbolize that by Z. And so if we know what that number is, we can automatically tell what element we must be talking about, because the number of protons is unique to each element. And we can find those values very simply on the periodic table. So an example here. Let's say we want to know which element contains 5 protons, which one has 10 protons, and which one has 34 protons. Well, to do that, all I need to do is look at the periodic table. So looking at the periodic table, the atomic numbers are these numbers on the top, which do not have decimal places in them. So the element with 5 protons is boron. The element with 10 protons is neon. And the element with 34 protons is selenium. Now, one of the most important things that we're going to need to know about chemistry in general is that in any chemical reaction, we never see protons being moved around. And if protons can't move around, what does that mean? Well, it means that any atom that you begin a reaction with has to be the same atom at the end of the process. So if an atom begins a reaction with 6 protons, if we go and look on the periodic table, 6 protons would mean it's a carbon atom. It still must have 6 protons at the end of the reaction. Those can never move around. So based on this information, is it actually possible to change lead into gold? The answer to that would be no. Lead and gold are different elements. They have different numbers of protons. So by using a chemical reaction, since we can't move protons around, they don't interchange at all in chemical reactions. If you start a reaction with lead, you're going to end with lead. It cannot turn into gold. Now, atoms that have no charge at all must have the same amount of positive charge as negative charge. I'm just going to call those neutral atoms. So neutral atoms have the same amount of positive charge as negative charge by definition. And so, therefore, because an electron is as negative as a proton is positive, what that means is in any neutral atom, the number of protons has to equal the number of electrons. So I just said a moment ago that carbon has 6 protons. So carbon should also have 6 electrons to be a neutral atom. Any atoms that do not have the same number of electrons and protons will have a charge. If the atom has more electrons than protons, it will be negatively charged. And if it has more protons, which are positive, than electrons, it will be positively charged. So whenever we have these charged atoms, we use the more specific term ions. Now, ions can appear confusing when we first start learning them because they seem a little bit backwards in the way that we write their formulas. So let's say for a moment that an ion has 1 more electron than it does protons. Is it going to be negative or positively charged? Well, if it has more electrons that are negative, that means it will be negatively charged. What if an atom loses 2 electrons? So you're assuming it starts with the same number of protons as electrons, and then it suddenly loses 2 electrons. Now you have more protons than electrons, so the atom would be positively charged. It'd be a positively charged ion. For every electron that an ion has more than it has protons, we will indicate it with a minus sign as a superscript. A superscript meaning like a power of 10. It'll be up and to the right of the number. And similarly, for each electron an ion has less than protons, we indicate that with a positive sign as a superscript. And we will generally put numbers in front of these signs to give us an idea how many more protons or electrons a given ion has. So let's go ahead and look at a few simple examples. So a neutral bromine atom, how many protons and how many electrons does it have? We looked that up on the periodic table. So bromine is Br. So take a moment and look on your periodic table, and you'll see that bromine has atomic number 35. If it's 35, that means it has 35 protons. And if it's neutral, that means it has 35 electrons. We will always assume neutral unless told otherwise. Let's say we add 1 electron. So it will still have 35 protons, which means it's still bromine. But now it has 36 electrons. So instead of being just a plain old bromine atom, it is now a bromine ion. And we can symbolize it like this, with Br and a minus charge there. That's more common. Sometimes, however, you will see Br written with a 1 minus or any other negative ion. It's okay to write 1 minus. I usually just write a minus sign. What about aluminum? We do the same thing as we did with bromine. We go to the periodic table and look it up. Aluminum is Al, and you'll see that it has atomic number 13. So that means we have 13 protons, and if we're neutral, we have 13 electrons. Aluminum, as we'll find out, likes to lose 3 electrons in the reactions in which it engages. So if it loses 3 electrons, How are we going to write that? You write the symbol Al, and then losing electrons means you're going to be positively charged. So it will be Al 3 plus. So you see, this is why I said it's a lesson in thinking backwards, because losing something gives you a positive charge. You're losing things that are negative. And same idea here. If you're gaining electrons, you're gaining negative charges. That's why it's negative here. I'm going to go ahead and end this part of the lecture right here. But the topic continues right into the next video lecture, which is beginning with neutrons and isotopes. So you want to make sure that this material here is fresh in your brain for when you start the next video. Thank you.